Okay, today we are going to start a new chapter that is called Analytical Solution to Navier Stokes Equation. So far we have discussed um, several kinematical and dynamical equations that involves fluid flows. Right. So far we have not discussed about the solution strategy that we are going to take uh, if we have to tackle this full Navier-Stokes equation. The problem with this full Navier-Stokes equation is it is highly nonlinear in nature. Okay, and that is why it is very tough to solve. If, nevertheless, what we are going to do here is in this particular chapter, we will take up few standard problems which involves no nonlinearity in the equation and which allows us to seek the analytical solution of Navier-Stokes equation, and which is advantageous for us also because by just hand calculations we can actually get the analytical solution of modified or so to say reduced Navier-Stokes equation. Although the full Navier-Stokes equation we cannot solve still to the till date, and that is why we take help from computer programming and uh, computational methods. That is why there is another subject called computational fluid dynamics, and we will take help to solve the full Navier-Stokes equation in computational fluid dynamics courses. Okay, but in this particular course we are going to seek the analytical solution through hand. Okay, and we'll see that how beautiful this would look if I try to solve this Navier-Stokes this basically the reduced Navier-Stokes equation in this chapter. So I will start discussing with some introduction, and then I'll start taking up few cases that involves no nonlinearity in the equation. So basically, nonlinearity comes in the Navier-Stokes equation because of its advection term. So the advection term that is sitting in the left hand side of the Navier-Stokes equation, which is u dot del u, which often uh, give rise to the nonlinearity in the differential equation. And because of this nonlinearity, it is tough to solve. But uh, in some scenarios, such as your steady flow between parallel plates, such as Poiseuille flow and Couette flows, or steady flows in a pipe, circular pipe, all those scenarios, we actually can get rid of nonlinearity uh, from this Navier-Stokes equation. Okay, and once we are once we are left with without this nonlinearity in the equation, we can actually uh, go for a very simplistic approach towards the solution to this Navier-Stokes equation with the prescribed boundary conditions and initial conditions. Okay, I will discuss about parallel plates such as Poiseuille flow, Couette flow. Okay, Poiseuille flow is nothing but there is a flow between two parallel plates with pressure gradients or without pressure gradient. It can happen, and you will have a parabolic profile inside those two parallel plates. In Couette flow, this is similar to Poiseuille flow in two parallel plates. One of the plates, without applying any pressure gradient, one of the plates, if you start moving, one of the infinite plates, I mean, you have to assume that those plates are infinite, and you have to move one of the plates with certain velocity. And in this flow scenario, I mean, in this particular scenario, in this dynamical condition, whatever the flow field that you will see, and that give rise to this fluid flow phenomena called Couette flow. And we the reason why we are reading these flows, because it is easy to get the analytical solution out of this flow scenarios. Next is steady flow in pipes. So in pipes, unlike this Poiseuille flow, we have circular pipes, and in these circular pipes also we will have some sort of since this is a three-dimensional case, so instead of parabolic profile, you will have a paraboloid profile in this particular scenario, and in this case also we will be able to find the analytical solution for the reduced Navier Stokes equation. We'll also look upon later. We'll also look upon the steady flow between concentric cylinders, which is also equivalently known as Taylor-Couette flow. Taylor-Couette flow, and the large implication or the large application of Couette flows are in your lubrication or in your journal bearings, where you have a shaft that is rotating around another another coupling, and where the lubricants or the fluid inside between these two bearing and the coupling may give rise to these sort of flow scenarios. Next, we will take upon some transient cases as well. So far, we have talked about steady cases. Transient cases also we could actually think of seeking the analytical solution of Navier Stokes equation transiently. Here, the word transient means you have not achieved your steady state conditions. So you have your all the unsteady terms will be intact there. Dou u by dot t and dou v by dot t will be there, and we'll look upon closely how these things work. So transient fluid flow scenarios, you are not going to ignore your unsteady terms, and including these transient terms, we are going to seek analytical solutions as well. And the transient impulsive starting plate. So basically, this is also called Stokes' first problem. Okay, first, this is essentially you will have a plate, infinite plate, and you have a fluid domain that is resting on top of it, and you start accelerating or you start pulling this plate in some direction with some impulse. So how transiently your fluid flow profiles that will you will observe in this fluid region. Okay, so this typical scenario is also called Stokes first problem. We can also have Stokes second problem, in which we are going to oscillate this plate with certain frequency, maybe some sinusoidal frequency with a sin omega t or some with time, and we are going to oscillate it, and we are going to seek the solution of this sort of fluid flow scenario in transient way. You can get the solutions like this. I don't know, we will when we reach on this particular problem, we'll look upon this in details. Lastly, we can also think of some analytical solution. We can also expect some analytical solution in our low Reynolds number cases. Okay, so in low Reynolds number, what is the advantage? Your at a very low Reynolds number, your viscous effects are dominated over the inertial effects, and thus you are actually able to get rid of your advection terms quite significantly. Okay, so all the low Reynolds numbers flows are often called as creeping flows, or it is also called Stokes flow. Okay, and usually in manufacturing industries, several presses, you will find this sort of flow scenario. Okay, and we'll more precisely in creeping flow, we will actually try to look upon the flow over some sphere or some cylinder, and we are going to seek some solution. Lastly, we have a Helle-Shaw flow. This is one more case for spherical case, and it is a quite complex phenomena. and we'll also look into details at later section. But let us start with the steady flow between parallel plates, and we are going to try to seek the solution. So as I told, because of the presence of the nonlinear advection term u dot, so basically u dot del u, essentially this term is sitting on the left hand side of this total derivative term. Let me expand this term and let me write uh, in the expanded form as rho dou u by dou t plus u dou u by dou x plus v dou u by dou y w dou u by dou z is equal to minus. So let me write all the x momentum, y momentum, and z momentum equations of Navier Stokes equation first, and let me go through the details of what exactly this signifies. So we have already looked upon this vector equation and the tensor notation. In tensor form, we have also looked upon the full Navier Stokes equation. Now we are going to deal it with individually. Individually, each equation we are going to deal with and to seek the analytical solution. The idea behind this is from the boundary conditions or the initial conditions. When you impose the boundary or the initial conditions, some of the terms may no longer be valid or may be omitted because of the boundary and the initial condition and the flow physics that this particular scenario possesses. Okay. My x momentum equation reads as rho du by dt plus u du by dx plus v du by dy plus w du by dz is equal to minus dou p by dou x, your pressure term is the source term, plus rho gx, if at all in x direction you have gravity, if at all it is not, it goes to 0, the body force goes to 0, plus mu times the dynamic viscosity times the Laplacian of u. So Laplacian of u I can write dou 2u by dou x square plus dou 2u by dou y square plus dou 2u by dou z square in the full 3D, three-dimensional sense. Let me also write y momentum equation for the clarity. So this reads rho dou v by dou t. So notice that your the scalar variable u, the x velocity is replaced by y velocity v, and this is usual u dot del u, right? This is how you write the advection terms. So these three terms are essentially the advection terms, and this is essentially nonlinear in nature. So somebody tell me why I am writing u dou u by dou x as a non-linear term. Can somebody comment on that? Or do you have any idea why I'm telling non-linear? Because how do you define a differential equation be a non-linear or linear? How do you define that? आप लोग को पता है प्रभात? डिफरेंशियल इक्वेशन की नॉन लिनियरिटी आप कैसे देखते हैं? आप लोग कभी पढ़े हैं इसके पहले? हाँ नहीं, आई मीन जस्ट एटलीस्ट आंसर yes or no so that I can tell. Yes, no?
No, sir.
No,
No,
sir.
sir.
Okay. So the thumb rule for identifying the non-linearity in the differential equation or the partial differential equation is you have dependents. So let's suppose you have variables. You have dependent variables and independent variables. Dependent variables, and you have some independent variables. Okay, and in this scenario, what are your dependent variables and what are your independent variables? So dependent variables that depends upon some independent variables. So your independent variables are, so you are plotting your things on x-axis or y-axis or z-axis or with time, right? And what you are plotting? Your u velocity, your v velocity, right? And w velocity, right? So u, v, w's will be your dependent variables, and you are plotting on what? X-axis, y-axis, z-axis, or z-coordinate. So these things are independent variables. Okay, so basically u depends on your independent variables, and t also. Okay, so notice that u, v, w are dependent variables. Now let me clarify that your partial differential equations uh, will be non-linear in nature when there is a multiplication of dependent variables. So either dependent variables or their derivatives as well, or derivatives of dependent variables. Okay, so what does it mean? So whenever you see your term, I mean any flow scenario, if you see this term u times v, or u times u, okay, or u times w, also u times dou u by dou x, or you see u times dou v by dou y, anything. Okay, so you are multiplying with your dependent variable with the derivative of that dependent variable. So all these terms will lead to non-linearity in the equation. Okay, so what is the physical meaning of non-linearity? Basically, that I want to tell. The problem with linear equations, non-linear equations are, so in linear equations you may find several solutions, and the overall solution, the total solution can be the sum of the linear combination of all those solutions. You can actually do the superposition. Your superposition principle is valid. You can actually do the superposition, or the sum of individual solutions can give you the total solution. Whereas in nonlinear equations, this superposition things are no longer valid. Okay, because of this, these terms sitting over there, because of this multiplication terms, you may not do the superposition to seek the solution. Okay, so that is why nonlinearities are often very tough to handle. Okay, and in general we leave that behind to the computer programming, or computational fluid mechanics or fluid dynamics uh, courses to handle that. But in this course, in this advanced fluid mechanics, we are going to seek solutions once we are get rid of this nonlinearity, and then we can very peacefully I can do the solution. Okay,
सर
so हाँ, tell me.
सर ये जो आप लिख रहे हैं ना वो लेग हो रहा है, आप लिखने के बाद जो स्क्रीन पर आ रहा है
Okay,
ऑडियो पहले आ रहा
I think there is a net problem. So here, so at my home net problem is not there. I'm currently I'm at campus, so I'll try to write very slowly. Okay, so here, so this this slide is visible. So this second term, third term, and fourth term, you can see there is a multiplication of dependent variable with its derivative. So that is why these three terms will raise to non-linearity in the equation. Right? Okay. So it will be sitting over there. Let me write the y momentum equation. So u dou v by dou x, I should write that v dou v by dou y plus w dou v by dou z is equal to minus dou p by dou y this time plus rho g y, if at all the body force is acting in y direction, plus the surface forces, or this because of the stresses, you will have this Laplacian over here, or the viscous term mu dot 2 v by dou x square dot 2 v by dou y square dot 2 v by dou z square. Okay. Lastly, the z momentum equation. Let me write for the sake of come for the sake of completeness. Rho dot w by d. This is the third velocity. U times dot w by dot x plus v times dot w by dot y plus w times dot w by dot z is equal to minus dot p by dot z plus rho g z, if at all there, the body force in z direction, mu times dot 2 w by dot x square dot 2 w by dot y square plus dot 2 w by dot z square. So this is the complete full Navier Stokes equation I can write in individual axis, in x-axis, in y direction, and in z direction. Okay. Now let me tell you the preface of. Tell me.
सर नेवियर स्टोक इक्वेशन में जो ये नेगेटिव वैल्यू हम प्रेशर की लेते हैं ना सर,
हाँ,
वो क्यों लेते हैं?
सो ये प्रेशर टर्म तुम्हारा सी हम लोग जब लास्ट चैप्टर में हम लोग ये डिराइव कर रहे थे, सो एक्चुअली डेरिवेशन से आया है. आई डिडंट डू एनीथिंग. ठीक है, आई डिडंट डू एनीथिंग. So it comes from the derivation actually, the minus sign. Do you guys remember? So what is my Cauchy's equation? So let me go back. What is my Cauchy's equation?
सर सर
हेलो सर.
Hello, I'm audible.
सर
So remember Cauchy's equation. Okay.
सर स्लाइड आई आ गई.
हेलो शिवम, प्रभात।
बोल भाई।
बस सर क्या देते रहे अभी?
મેસેજ કર્યો મેં સરને, બરોબર.
हाँ तो मैसेज करे कोई आई क्या लगे यार?
Prabhat, am I audible?
यस सर.
Now are you
सर इधर का नेट जो है, इधर का नेट का प्रॉब्लम हो गया था. So okay, हाँ, to answer your question, so let me start recording again. Oh, it's already recording. Fine. So do you remember we have started from Cauchy's equation? So in Cauchy's equation, we have whatever we wrote as our. Let me write
Sir,
that.
your screen is not shared, sir.
So
Sir, your
row,
screen is not shared.
my screen is not
visible.
okay, let me reshare it. Okay, is it visible now?
Yes, sir.
Is it visible? Okay.
Now
Yes,
so
sir.
visible.
Okay, fine. Thank you. So rho dui by dt is equal to rho gi plus dot tau ij by dou x j. Okay. So and this tau, we seek that for rest fluid, we will write this tau ij is equal to minus p delta ij. Remember in tensor notation. So this minus p I have taken because pressure is a thing that always works or applies as if you need to compress something. Okay, you have never seen pressure as this sort of elongation effect. The pressure will always have compression effect. That is why we took minus sign over here, and this minus sign has been propagated till this equation, and you find this minus dp by dx. Okay, have I answered?
Yes, sir. Clear, sir.
Okay. Okay, let me go towards what is the time now? 34. Okay, we have 10 minutes. So let me go to start with the solution for parallel flows. Okay. So the one best example of this sort of parallel flows is flow between two parallel plates. Okay. Let's suppose you have a free stream velocity with even magnitude of capital U that was coming. The air is coming nicely. Once it hits this point, because of no slip condition that arises at the bottom and the top flat plates, this the velocity at the end of this section or at the wall becomes 0 momentarily, okay, at every points. And what you can see is the fluid packet that is above towards that above to that fluid element at the wall is trying to getting is sort of pulled back by this this fluid element, and similar way at the top plate. So you can see you will have a profile that will look something like this. Okay, so till this region you will have some shear stress, shear effect on the in this region, and after that you will have, I mean, the shear effect has not been diffused in this region. Okay, the moment you go forward, this region, this the what you call the diffusive momentum, okay, the momentum is going to diffuse in the y direction as well. So it keeps on diffusing, and you will reach a section where these two section meets, and after that everything is, and there is no transient diffusion of momentum in y direction. Okay, so you will have a completely fully developed flow after this section, and before that it is called entrance length. So till entrance length you will have a transient velocity field, and after that you have fully developed field. So in fully developed section, what we see after how long, I mean, whatever long you go uh, in distance wise in x direction, your flow profile or flow velocity is not going to change. So u is not going to change with x. Okay, however, your u velocity is changing with y. Okay, u will be a function of y, but u will not be a function of x anymore once your flow is being fully developed. Okay, and this region, the region where your diffusion momentum starts propagating from the wall is called boundary layer region, and in this region your viscous effects are dominated over inertial effects. So viscous effects are more as compared to the inertial effect.
Download the paper, that is better, because then I cannot have a look at it.
Okay, now let me come back to our problem
from the email ID and
again for fully developed. I mean, let's suppose I am trying to seek. So what is my aim? So what my aim is to seek the steady state solution or solution means you are trying to find the flow fields such as velocity field, pressure field, all sorts of fields. Steady state solution flow between two parallel plates. And so this is your, these are your fluid elements over here. Okay, and let me first assume our coordinate system first. So let me go back to the figure first. So this is my x-axis. So let me do it with another ink. So this is my x-axis. This is my y-axis. And the length between these two plates are, let's suppose, 2b. Okay. What are the boundary conditions that you would expect? Okay. What are the physics that involves here? So you, once it is developed and steady state solution, so all your flow, unsteady flow physics, dou u by dot t, dou v by dot t, and dou w by dot t will become 0. Okay, u will be a function of y, you would expect, this is there. U will not be a function of x or z will not be a function of x. Okay, this will not come into picture. Your v velocity will not come into picture because there is no net. Once the flow field I mean the boundary has layer has been developed, or the fully developed scenario has come. After that, your v velocity will not be there. W velocity will also not be there. W will be into the plane. Okay, v velocity will be there if at all you are seeking the solution in your boundary layer. Boundary layer when boundary layer entry length. Okay, till then you will have some v velocity as well, but for the time being we are since we are looking at the fully developed section, we're not going to look into v. So let me start with our Navier Stokes equation and let me write it again. So my first x-axis Navier Stokes equation reads as dou u by dou t plus, so this is per unit volume, so rho dou u by dou t. Okay, u dou u by dou x plus v dou u by dou y plus w dou u by dou z is equal to minus dou p by dou x plus mu times dou 2u by dou x square plus dou 2u by dou y square dou 2u by dou z square. Okay, one more thing, we take the generic case and we think that we also assume that there is a pressure gradient that is applied pressure gradient is there since the beginning. Okay, so there is a pressure gradient. Because of this pressure gradient, either by the pressure gradient, I mean the flow is happening obviously, unless until there is a pressure gradient in the pipes the flow will not occur. So yes, there will be a pressure gradient, so dou p by dou x will be there, but yes, dou p by dou y and dou p by dou z will in this particular scenario we are going to ignore that. So pressure is not changing with y or z, but yes, pressure is changing with x. That we will assume there is an applied pressure gradient. So applied pressure gradient is there. So we will take this some constant pressure gradient g we will take. So okay, that's the another story, but we'll start it with here. Since this is a steady state problem, so dou u by dou t will go away. Let me write it. So you have to write assumptions in this manner. So since this is steady, so that is why this term goes away. Okay, so what about u and u dou u by dou x? So u velocity will be there, but u velocity, the gradient of u velocity with x will not be there. Why? Because of fully developed scenario. So your flow, x velocity flow is not changing when you traverse in x direction. Okay, what about dou u by dou y? Dou u by dou y will be there, but here v velocity will not be there. Why? Again, fully developed scenario. Okay, there are no net velocity in v directions because your plates are fixed in space in y direction. Okay, so there is no net v velocity that is happening in this scenario. Similarly, there is no net w velocity is also not happening, but du by dz may be there, may not be there, but because of this it goes to 0. Okay, so we are left with dp by dx will be there, dou u by dou 2u by dou x square, will it be there or not?
No, sir.
Okay, why? Because since u is not a function of x, so its second derivative will not be again be a function of x, right? So this goes away, but you are left with this only. Okay, so now summarizing the x momentum equation, you can write as 0 is equal to minus dou p by dou x plus mu times dou 2u by dou y square. So we have one equation. Okay, one more equation we can think of y momentum equation as well, and let me write that also. Rho. So somebody tell me. So you should have a good practice of writing Navier Stokes equation, full Navier Stokes equation all the time, because you will be needing every now and then. So dou v by dou t plus u dou v by dou x. Okay, dou v by dou v by dou y, w dou v by dou z is equal to minus dou p by dou z this time, plus mu times dou 2u by dou x square plus dou 2u by dou y square plus dou 2u by dou z square. Okay, if you think carefully, this is an unsteady term. This goes away since we are talking about steady state solution. Okay, u velocity dv by dx, since v velocity is not there, so there is nothing. Ignoring this, v velocity is not there, w velocity is not there. Okay, so this is my v now, this is v, sorry, this is 0, this is 0, this is 0. So you are left with dou p by y z. I am writing, so this is y, dou p by dou y is equal to 0. So we see that inherently it comes that pressure in your fluid flow scenario also, pressure is not varying with y. So whatever pressure you have here, it will be propagated everywhere in this particular line. It's not changing. Okay, but yes, pressure gradient is there if you traverse in x. So I think we have so we will keep these two equations and we'll try to apply the boundary condition. Let me take 1 more minute and then I'll leave this class. So what are my boundary conditions? So boundary condition is such that you have x coordinate over here. So at to 0, you have u velocity that goes to 0. Another boundary condition at this particular bar at 2b distance, at x is equal to 2b, again you have u is equal to 0. Okay, when you apply that in your equation, what are your equation? 0 is equal to minus dou p by dou x plus mu times dou 2u by dou a square. So can you apply it, or let me integrate it once again? Dou 2u by, so I can actually write now, since everything has been replaced, so I can replace it with by, not by partial differential, by the total differential. Rather than dou u by dou y, I can write du by dy. Okay, so this is nothing but 1 upon u dou p by dou x. So this dou p also I can relieve it as dp by dx. Okay, I will integrate it one time. So du by dy is equal to 1 upon u dp by dx times u plus c1. I can integrate it again twice. So I can come up with u is equal to 1 upon mu dp by dx y square by 2 plus c1 y plus c2. So this is your solution that you will get. You have two constants and you have two boundary conditions, and if you apply that, you will come, and this I mean, just do a quick homework. If you apply this boundary condition, insert these boundary conditions appropriately, you'll get u as a function of y, your solution. So see how from full non-linear equation we are able to get actually some nice solutions, nice analytical solutions, right? We'll in the next class we'll also look upon several other cases. Okay, so far any doubt? No, yes. Okay, I hope there are no doubts, so we can stop the